In this example, we're going to determine the vapor composition that's in equilibrium with a liquid whose composition is given. We're also given the pressure. We have to determine the temperature for vapor-liquid equilibrium. And we're given the Wilson parameters. So we're going to model the non-ideal liquid using the Wilson equation. And this is an equation that assumes the local compositions can be different from the bulk compositions. And for a number of liquids is a good fit. So what we're going to do is write down the equations. You'll see that the relationship between the Wilson equation and the modified Raoult's law is such that we really want to solve this numerically. And so what I'm going to do is list the equations that we need to solve numerically. And because of this temperature dependence and the saturation pressure, this is one of the equations. This is the second equation. These are the saturation pressures for the two components, just the Antoine equations. And so the modified Raoult's law says the mole fraction, component 1 in the liquid phase, times the activity coefficient, component 1, and the saturation pressure is equal to the partial pressure in the gas phase, which is the mole fraction of component 1 times the total pressure. Now we have the exact same type equation for component 2. And so equation 3, equation 4, the other equation we're going to need is that the mole fractions that we determine have to add to 1 in the gas phase. I'll call this equation 5. And so the activity coefficients we're going to determine from the Wilson equation relations. So the log of gamma 1 is equal to minus the log x1 plus x2. It's one of the parameters that we have. The Wilson equation will calculate, plus x2 times another parameter in the Wilson equation. So this is equation 6. And likewise, I'm going to have a very similar equation for the log of gamma 2. That's equation 7. Notice it's not exactly the same. Of course, x1 is replaced by x2 everywhere, but we have a minus sign here. Now, this is equal to V2 over V1. These are the parameters that are given in the problem statement. And the exponential, again, parameter A12 is given in the problem statement. And likewise, similar expression. And we have one more equation, namely, what's the value of W? I'll write that down. So W is in terms of these parameters, and x1 and x2. And so we have 10 equations. And then we should have 10 unknowns, and it's important to check this. So our unknowns are the mole fractions in the gas phase, the equilibrium temperature, the saturation pressures of the two components, and then the parameters from the Wilson equation, and then the activity coefficients. So we have 10 unknowns. And we have 10 nonlinear equations. We're going to just use the regression to solve for these. In this case, I used polymath, but clearly other techniques are possible for solving this. Polymath happens to be fairly straightforward. So what I'm going to show you is the results in the polymath program. Here's the output from the polymath program. The mole fractions that we're interested in solving for. Polymath reports them to more significant figures. In reality, we'd probably say that y1 equals 0.86 and y2 equals 0.14. And the temperature, probably not accurate to 3 significant figures. Temperature 344 Kelvin. And then showing here is the polymath program, where essentially it just writes the equations with all the terms on the right side as some function of one of the 10 variables. It doesn't matter which one as long as we have all 10 variables. And then the program sets these functions equal to 0 and finds the appropriate parameters. And in the program, you need to make initial guesses of the values to make the polymath program work. But you can see here are all the commands in the polymath program to determine now the equilibrium temperature and the mole fraction using the Wilson equation.